choose the wrong database, and every future feature pays interest on that decision. Start with the data behavior, relationships, transactions, access patterns, growth, and hotspots. Basic SQL versus NoSQL comparisons miss the real question. What must stay correct under traffic, change, and failure? By the end, the decision should feel practical. We will compare SQL and NoSQL through one production lens: query shape, consistency needs, scale pressure, operational maturity, security boundaries, and business risk. SQL databases are built around structured relationships. Tables, keys, constraints, joins, and transactions let the database protect facts that must agree with each other, especially when many parts of the business touch the same data. NoSQL is not one thing. Document, key value, wide column, and graph stores make different trade-offs, but they share a pattern. You usually model data around the access paths the application needs most. The right model starts with the hottest reads and writes. If the application constantly asks for one customer with recent orders, that shape may be different from a finance report joining thousands of rows across multiple entities. A slow SQL design can be fixed by better indexes and cleaner queries. A slow NoSQL design can be caused by the wrong partition key or a document that grows without bounds. The category does not save you from bad modeling. A database is never isolated. It sits behind APIs, workers, dashboards, reports, backups, identity controls, and incident processes. Choosing a database is choosing how all those boundaries will behave. A strong SQL architecture often uses the relational database as the system of record. Services write through controlled transactions, reports read from replicas, and the model makes shared business rules explicit. A NoSQL architecture often prepares the view the application needs. Instead of joining at read time, teams duplicate selected data into documents, partitions, or indexes that match the request path. In serious systems, the answer is often not pure SQL or pure NoSQL. A relational core can protect money and inventory, while NoSQL views, search indexes, caches, or event streams make read-heavy experiences fast. Take one order. The customer expects inventory to be reserved, payment to be recorded, and the order status to be truthful. That single business action tells us which facts must be correct together. In a SQL flow, the service can update related rows inside a transaction. If payment recording fails, the order and inventory changes can roll back together instead of leaving the business in a half-true state. In a NoSQL flow, the team may write an order document and publish events that update customer views or fulfillment views. The read path can be fast, but the design must handle duplicates, ordering, and eventual consistency. The customer does not care whether the backend is relational or document-based. They care that the order is correct, the page is fast, support can audit what happened, and the team can recover when something breaks. If the system allows oversold inventory, duplicate invoices, or missing status updates, the customer experiences it as a product bug. Consistency is not an academic property. It is part of the user promise. Scaling a database is not only about bigger machines. SQL systems may need replicas, partitioning, or sharding. NoSQL systems may need careful partition keys and capacity planning. Either way, scale becomes an operational design problem. NoSQL does not eliminate schema. It moves some schema responsibility into application code, validation, migration jobs, and compatibility rules. SQL makes schema explicit. NoSQL often makes it operational. The database choice also chooses the dashboards. SQL teams watch slow queries, locks, replication lag, and backup health. NoSQL teams watch hotkeys, throttling, stale projections, and stream lag. you operate the failure modes you selected. Database access is one of the strongest security boundaries in the system. Senior teams design least privilege, encryption, audit trails, secrets management, and data classification before the database becomes a shared shortcut. A team that chooses a database also chooses backups, restores, index maintenance, capacity planning, upgrade windows, and ownership. The best technical choice can still fail if the team cannot operate it well. Application deployment and data changes must be coordinated. SQL migrations, document version changes, backfills, and read model rebuilds need compatibility windows, feature flags, rollout plans, and rollback decisions. Strong teams rehearse the ugly moments: deadlocks, failovers, hot partitions, bad migrations, corrupted read models, and slow restores. The decision is only production ready when the team knows how it fails. The senior review starts with the workload. What queries dominate? Which facts must be consistent? How fast does the data grow? What does the team already operate well? The answer comes from those constraints. SQL may give stronger relational guarantees, but it can demand careful schema and scaling work. NoSQL may give flexible shapes and distribution, but it can move consistency and schema discipline into the application and operations layer. Good teams do not argue abstractly for weeks. They prototype the real access patterns, load test the hot path, test restore, model failure, and review the migration plan before the database becomes expensive to change. The final question is simple. What must never be wrong? What must be fast? What can be eventually consistent? And what can your team operate under pressure? Choose the database that protects that outcome.